Hi, I'm Gary Conley. Today we'll be demonstrating the field methodologies used to develop the habitat characterization that we employed for the Department of Energy's ports facility in Piketon, Ohio. In order to characterize the habitats that exist within a study area, we wanted to capture vegetation plots. In this instance, we're actually using circular 10-meter radius vegetation plots, which will capture the trees, shrubs, and vegetation layer, as well as characterizing the soil and any habitat features that might be encountered. In order to do that, we establish a single point, which will become the center of our vegetation plot, which is indicated by the pole that we establish in the center. It has blue and red tape on it, in which we use a forester's prism in a non-traditional sense to overlap the two colors until we are exactly 10 meters away from the center. Circular plots are certainly much easier to set up than square plots and much easier to replicate when you are out in the field. If we were to do long-term studies of a study area, you would want that consistency in quantitative measures. Here today we're going to measure primarily the vegetation component of the ecosystem, starting with the trees, the forest canopy, the shrub layer, and the vegetation layer. Then we'll take a look at the soils and habitat features that might exist here on the site as well. Now that we've established our plot perimeter, we're going to measure the DBH, or diameter at breast height, of each of the trees located within the perimeter of the study plot. This is a sugar maple, which is exactly what you'd expect to find on a mesic slope. The DBH is taken at breast height from the lowest side of the tree. And we're at 17.8 inches. This sugar maple is 17.8 inches in diameter. This is a special tape designed specifically to measure the diameter of each of the trees. I certainly wouldn't measure linear measurements with this. Once the size of all the trees has been measured, we want to get some idea as to when the trees began to grow here and what the growth rate might be. One of the ways to accomplish that is to take a core from a sample of the trees. In this instance, we're choosing a white pine. This was clearly a planted pine, and we can get some idea of when this pine was planted and how quickly it grew in competition with the other species. In order to do that, we've chosen a tree bore, which we'll drill into the tree and try to hit the center of the tree so that we can establish a time in which this tree began to grow. Going in nicely now. Tightening up. Now I'd say we've hit the center here. Once the center is reached, the bore is backed out one full turn. The spoon is inserted down the shaft. And hopefully the core is removed. Not always so easy. And there we are. So once the core was taken from the tree, we did hit the center, and I can roughly count the rings using my hand lens. And I've counted about 55 or 60 rings here. So these white pines were planted about 55 or 60 years ago. And I do notice that there are periods where the tree was growing faster at times and slower at times based on the width of those rings. Of course, the tree grows, as it grows faster, the rings are wider, and they're much more narrow in years where it's growing slower. This could indicate differences in competition or light availability. Once all the tree measurements are made and a couple of cores taken, it's time to measure the shrub layer. The shrub layer consists of anything that's taller than my knee and less than 1 inch dBH. In this case, we've got a patch of pawpaws growing. They're all fairly small due to a new forest gap that's opened up as that white pine has recently fallen. In order to measure the shrub layer, we use a caliper and essentially measure the base of each of the shrubs within our sample plot. In this case, this pawpaw's about 1/2 inch in diameter, which is about the average size of most of the pawpaws in this patch. The other shrubs in this layer would consist of small beech trees, other small maple trees, and a handful of oak trees. The lowest layer of vegetation is the herb layer, and that consists of anything less than 1.5 feet tall and is typically composed of herbaceous species. We do have a number of woody species that are incorporated in the vegetation layer quite often, and in this case we have some raspberries and blackberries, the rubus genus. But for the most part, we do see herbaceous species. We have a wild yam and some Christmas ferns here, comprising a large portion of the sample. And we also have some carex species. The sample is a 1 square meter sample area that we randomly throw out in all 4 quadrants of the vegetation plot. All of the species within that 1 meter hoop are identified and quantified in the terms of the vegetation cover within that circle. The total vegetation for the sample is also noted on the field sheets, and any species or samples that can't be identified, 2 species, are collected and placed in a bag with what we call a voucher. Quite often grasses and sedges can't be identified to species in the field, so they're commonly collected. And in this case, we do have a grass species. We'll just take the above ground vegetation and we'll go into a bag to be put under a microscope and looked at more closely to identify it to the individual species if possible. Quite often carexes and grasses require that the plant be in fruit or in bloom in order to recognize all the pertinent features of the plant itself to identify 2 species. So quite commonly you'll have vegetation within each of the samples that can't be identified 2 species at that particular time of year. So to comprehensively characterize vegetation of any sample, it's best to collect at multiple times of year. And on the Ports facility, we visited both in the spring and the fall to almost all of our vegetation plots to most comprehensively characterize the vegetation that was there. This is a pretty typical vegetation cover for a mesic slope. We have some jewelweed incorporated in with our sample here, indicating that there's some soil moisture, and a lot of the pine needles created sort of an acid condition to the soil, so you have some more acid-loving species here as well. Once the vegetation is characterized, the tree layer, the shrub layer, the herb layer, we look for opportunities for wildlife to utilize the habitat. So we look for habitat features such as the number of holes in standing trees, cavities in which birds could make nests or small mammals. We also look for trees that have loose attached bark, such as shagbark hickory or a sycamore tree, provide opportunities for bats to find habitat. We also look for rocky holes and crevices in the ground for ground nesting species and perhaps amphibians and reptiles. We look for any light soil with burrows, indicating that perhaps small mammals have an opportunity to dwell in the subsurface, as well as raptor perches. These would be opportunities in the upper part of the canopy in which a raptor could land, such as a hawk, could land and observe the habitat and wait for feeding opportunities on the forest floor. These are all elements that play into the functionality and complexity of each of these ecosystem habitats. And finally, to characterize the habitat here, we capture some of the physical features of the study plot itself. In this case, we will be pulling a soil sample using a 12-inch soil probe. Simply inserted and pulled out, we end up with a very nice cross-section of the soil underneath our feet here. So the soil sample that we just pulled from this particular location includes a very sandy soil. We're high up on the slope, and it's pretty indicative of weathering sandstones. A lot of the outcroppings here are shale and sandstones, and we see this sand accumulation from that weathering process over ages. But we also see here on the top an organic horizon, which is an accumulation of all the organic material that's been falling, on the forest floor here, such as leaves and twigs, and of course rotting carcasses, perhaps. That organic horizon then decays down to the uppermost horizons where the roots of all the plants and trees are located, and further down into a B or subsoil horizon. In this case, consisting of a large portion of sand, but a fair amount of silt as well. Now that soil type could vary pretty dramatically from location to location throughout even the sample plot. So a lot of times we'll take a couple of soil samples from around the plot if we do think there's some diversity there. In order to finally characterize the plot itself, we'd actually take a slope and an aspect. It'd help us to characterize the physical state of the plot as well. In this case, we're on a north-facing slope, and there's a clinometer feature on this particular compass in which we can identify the angle of slope, in this case about 15 degrees. All of this data collected helps us to formally characterize this habitat physically and vegetatively, produces a data set with many attributes that could be queried in a number of ways to one, map the different types of habitats that could be found in the study area, but also to determine what species might be occurring here, to analyze that data spatially and ask a number of questions of that data for years to come. It can also provide a baseline data for determining the long-term changes of that ecosystem and the overall impacts to disturbances of various kinds. In the face of climate change, it's quite valuable to collect as much of that data now to determine how that might impact our forests and ecosystems in the long term.